Today we're going to take a look at how to make an angle of arrival measurement using the VSA software's angle of arrival measurement capability. What you can see here is a multi-channel capture. We can see four channels. Here in yellow, we have channel 1, here in green, channel 2, in blue, channel 3, and in red, channel 4. And what we're going to do is make a calculation either using time domain or phase interferometry to measure a logical angle of arrival for, say, a given emitter with reference to our system under test, being the oscilloscope in this case. So what we're doing, just to go over the measurement setup a little bit here, is we're capturing several hundred pulses. And in this case, we're using our segmented capture feature so that each segment is about 1.4 microseconds, and we're capturing 300 segments. So this gives you a total acquisition time of just under 500 microseconds, but based on the knowledge of the PRI of our signal itself, this is over tens to 20s of seconds. And so this is really important given how long it takes for emitters of interest to change angle over time. So we have a center frequency of 6 gigahertz and a bandwidth of about 100 megahertz for our particular signal today. So what we can see is we can start to play this signal and we see its amplitude profile that change over time, and this is indicative of an angle of arrival type change. We see a little bit of a time domain effect here towards the end of this scenario on channel 4 that may cause some issues. So we want to look and see if we can find a reason for that or how that manifests in the angle of arrival measurement. Overall in our pulse table, let's make sure we could see interesting parametrics. So we're interested in amplitude. We don't care about droop yet or overshoot or ripple. For time domain, we're going to look at the rising edge. This is when each pulse occurred in time. And we're going to look at pulse width and PRI. We're going to take that off. We're going to look at the average frequency. We're going to look at the average phase. And then we're going to look at the angle of arrival, both azimuth and elevation. And then we're going to hit OK. And you'll see really quick here that this table changes its columns pretty quickly. So we'll pause here for a moment, and we'll see that we can see the pulse detected, the segment number of the capture, and then the modulation detected, the amplitude, and a few others. We still have droop on there, so we'll just take that off. Okay. And here we can see PRI. And this PRI is really important because functionally what we're doing is we're capturing every 120th pulse of our signal of interest. And the signal that we're getting is generated by a Keysight UXG Agile Vector Signal Generator. And it's sending out a strobe or a trigger pulse every 120 milliseconds or every 120th pulse. Because the actual signal of interest is about 1 microsecond wide with 1 millisecond of PRI. So that's just important to understand the logical time. And we can see this overall capture of about 300 pulses. If we maintain a view of the rise edge, we're capturing about 35 seconds of time. So what does this look like, or how do we make the measurement? Well, under Measurement Setup and Pulse Properties, we can now go into the Analysis tab and select Angle of Arrival. And we actually already have it activated. And what's really useful for users is that you can change antenna orientation. In this case, we have 4 antennas, and they're oriented in this 3D plot here. We can see antenna 1, 2, 3, and 4. And the position of these with respect to the origin is very handy in this table here. And we're measuring this based on knowledge of our waveform at 6 gigahertz with a 1 lambda wavelength, which equates to 50 millimeters spacing in between each element. And so based on that information, we can deduce the XZ position because these antenna elements are in the XZ plane, and Y is looking forward and Y negative is looking backward from our system under test. And we're choosing the delta phase or interferometry method. And so what this allows us to do is now we can add a few extra traces. We'll add 2 extra traces here. We're just going to reposition our windows since we already looked at our time domain and our parametrics. and we're going to select trend lines. And these trend lines allow azimuth as well as elevation information. So here's elevation, and we're just going to make this really easy and kind of move our windows around, which is convenient for any user with the VSA software. And we're going to separate our azimuth and elevation trend lines. And we're going to hit play, just so you can see that it's a live updating measurement. And we see some phase discontinuity here, and that's due to this quick phase discontinuity jump that we have built into our scenario of interest. So I'm going to select pause again, and we're going to use the marker capability to really understand the start and stop angles of this particular measurement. And you can see as I'm moving my 2 delta 1 marker in my azimuth trace, it's moving at the same time in my elevation trace. And that's because I have my markers coupled, which you can do through the marker menu here. So this 2 delta 1 is making a delta measurement from this location with respect to marker 1, which we have here. And to make that measurement or see what those marker readouts, we can go down and look at our marker window down here. And they're color coded. So if we look at azimuth, which is in fuchsia or purple here, they're color coded. So our marker 1 is at minus 13.8 degrees, and that's our absolute phase, so to speak. And then our delta measurement to measure what's the slope or how far did I change over time in terms of angle, in this case is 28.1936 degrees. And similarly, we can look at elevation. We started at 15 degrees and we're ending at a change of 28.2571 degrees. And this corroborates what we expected, because based on our 4-channel UXG vector signal generator scenario that we created with our multi-emitter scenario generation tool, or MESG, we created a platform that is changing in azimuth from negative degrees to positive degrees. So it's coming from left to right. And the scenario we created is actually minus 15 degrees to plus 15 degrees. Secondly, in terms of elevation, it's going from a positive elevation to a negative elevation in terms of degrees. So it's moving down from looking up to moving down. So the combination of these gives us a 2-dimensional analysis of how this pulsed signal, this multi-channel pulsed scenario, is changing over time in amplitude and phase, and it's emulating a system under test, translating from the upper left as we're looking forward to the lower right. And this is very useful for electronic warfare and radar simulations to accurately test devices under test like radar warning receivers, to make sure that they can accurately find where a given radar threat is with respect to bore sight in this case. So I hope this was really helpful in explaining the measurement setup, as well as some of the tools that we can use to measure and analyze angle of arrival within the VSA software. Thanks for your time.